So now to the first session. So the first session is mainly on sensors and sensor fusion. So it's the most techy, I think, session of the workshop. And our first presenter is Joe Paradiso. Joe Paradiso is an associate professor here at the Media Lab. And his work has ranged from sensors to X-reality to other things. And we're pleased that he could come and present. Thank you, Joe.
Thanks very much, Dale. It's really a pleasure to have all of you come here to visit us at the Media Lab. And my talk kind of, I guess, gives a little bit of our perspective, especially from the viewpoint of my group, on the kind of things that we do with sensors. We're very interested, certainly, in sensing nature. And of course, with Dale here, a lot of we've got activity that goes on in that area. But a lot of what we do is about sensing people and trying to basically get out context and figure out what people are doing so the digital environment that we're all building through ubiquitous computing can start to work to help people do what they want to do. And my group in particular does sensor networks. We're really a sensor network group, again, aimed at ubiquitous computing. And the way I see it, if you really want to kind of take the stratospheric view, is that the world is building this electronic nervous system. You know, we're putting sensors out. Sensors are following corollaries of Moore's law. They're getting smaller and cheaper and more capable. And you can throw a lot of processing behind it. Wireless gets to be more or less commodity. People are working at lower and lower power, scavenging energy. So you can start to deploy this infrastructure all over the place. You can start to get information from it to pretty much anywhere. And I think one of the big challenges that the whole computer science community faces is how to interface this whole world of human perception to this electronic nervous system. How do we graft this burgeoning nervous system that's being built out now across the planet, you know, certainly across cities, but also across nature environments, and graft that into the human? You know, how is that interface working? So my group has got a few projects that really kind of look at that, because I think it's going to be very pivotal as this all builds out. And this is one of the things that Dale mentioned that's really been driving some of the work of my group in the last few years. It's maybe a possible solution to this whole idea of interfacing machine to human perception. And one place it can play out is in a virtual world. In virtual 3D worlds, you know, we're very well suited to relate to phenomena we see because we live in a 3D environment. And especially when we work in built environments, sensors are at geographic locations, so we can manifest the sensor result as some sort of apparition in a virtual space. People have played a little bit with this with environmental sensing. A lot of you probably know the work of Deb Bestrin in the SENS lab at UCLA. Deb's a good friend of mine. She actually worked a little bit with people at the James River Reservation where they would visualize sensor data in different ways on Google Earth. So you could fly over and you could see the sensor data. Some of you may have even been involved in projects like this. It's starting to take off a bit. But we figured, let's go one extra step. You know, we live in 3D built environments. Let's make analogies to these 3D environments in a virtual space, manifest the sensor data in various ways through actuators, enable virtual constructs to project down into the real world, and then try to use this as a potential interface to, you know, basically bridge human and machine perception in different ways. So my student Josh Lifton started this work for his PhD thesis a couple of years ago. And again, we called it first dual reality, then cross reality, where you've got, you know, the real world. We only live in one as far as we know. And the virtual world, it can be many, of course. And you can tunnel information back and forth through the sensor networks that are being built. They're like little wormholes kind of pulling information and pushing it between these two continua. So here we have a virtual construct. This is an analogous real construct, and the data can flow back and forth, for example. It's a simple example. I just edited a special issue of IEEE Pervasive Computing. This is the flagship magazine for ubiquitous and pervasive computing. And it's all around this whole idea of cross-reality. So I invited people from all over to contribute articles about it, and we wrote a big article there as well. So if any of you are interested, I recommend downloading this off of the IEEE site. It's all up there. And of course, when you map from a real space to a virtual space, you don't have to map one-to-one necessarily. This is, you know, Josh looking at space-time objects, people, right? You can kind of mix things. So you can exaggerate the way an animator would exaggerate, for example. And so you can, when you browse it, things can pop out more easily. I'll give you some example of that in a second here. We've done different kinds of incarnations of this, but most of our work has tended to be in Second Life, which is a very well-known 3D virtual world. There are a lot of people there. There are a million, I think 10 million subscribers to Second Life, maybe more by now. Online at any given time, there are at least thousands or tens of thousands of people there. And you can very easily develop with it. So you can put together, this is the virtual MIT that's actually there. It's kind of dull and gray. There's not a whole lot happening, but these are the crazy Media Lab projects behind. So there's a lot of innovation taking place, certainly in Second Life in many ways. So we thought, okay, we can build our sensors, we can funnel into Second Life and then realize them in Second Life and take phenomena in Second Life and just funnel them back into the real world and realize them here. So we can begin to play already right away with this kind of a platform. And this is an example of what Josh did called Shadow Lab. Up here, he's got a virtual view of our building. And we have little sensor nodes located where these little, we call them data ponds, are on the map. And the fronds wave with motion. There's a motion sensor. If there's more motion nearby, the fronds will wave more, like it's a wind. The sound level is the ripples. If it's louder, there are more ripples. It's metaphorical, but again, it makes some sense. The smoke is the amount of electricity. These little sensors actually are little electrical power strips, and we can actually measure the current that you're pulling out of the power strip when you plug things in. So to see where you're pulling more current or using more energy, you can see more smoke. And they change color with temperature. This sphere is a way to tunnel information back into the real world. If Josh's avatar gestures to this and sends a message, it will come out of the speaker in one of the plugs. The height changes with light. If it's brighter, they're taller. So simple language. This crazy thing down here that probably has been distracting a lot of you guys is Josh's idea of this whole mixed metaphor thing, where you can take information from the real world and not just tie it to a built space, one-to-one, the way we did up here, but also tie it, for example, to somebody's avatar. So this is Josh's virtual representation, and he tied noise in the area outside of his office to his hair. So if it got too noisy out there, his hair would just go crazy in the virtual world. Now, whether that's useful or not, you can argue. But the whole idea of having some sort of a talisman that represents state of an individual or state of a particular thing that's important to you, it could be reflected through your appearance. So somebody goes and sees you in the virtual world, they have some idea what's going on in the real world. Even if you're not online at the time, you can have mobile devices sending some of this context over, figure out whether maybe you're reachable or not. Or they can even give somebody a talisman, a little object that reflects an identity. It's a virtual object. You can carry that with you when you look at that, and that shows you what's happening to somebody you know. You could certainly think of lots of tie-ins to nature with this as well. Now, this is work that happened a couple of years ago. Our group has proceeded and moved on from there. We've got a whole new sensor system we put into the Media Lab. You've seen them if you've wandered around here. We call them the portals because they're two-way. They're displays and speakers, but they're also sensors. We've got a little Linux board on here with a video processor. We've got a 3-megapixel camera on it, so we can actually analyze images. We can take MPEGs, JPEGs in real time, and also decode them in real time. We can do machine vision on it as well and send up features. It's got a TI DaVinci chip on it, dual-core Linux and DSP. And there's, of course, a display, so virtual things can manifest on the portal. But there's also a lot of sensors on it. We've got a little board that sits in back here. And that board can be standalone or it can run as a slave to the portal. And that's got a stereo microphone. It's got a little processor with DSP capability built in. It's got a motion sensor. It's got temperature, humidity. It's got a light sensor. Actually, I think it may even be a color sensor. It's got a IR. There are actually two kinds of IR on this to talk to little badges that we build. So if you have one of our badges on and you're in front, it can tell that you're in front, and you can communicate with the badge and download and upload data. So it's for face-to-face interaction. I'll say more about that in a minute. And there's also a little ZigBee radio. RF becomes more commodity now, so for a few dollars you can buy a chip from a company like Nordic or Chipcom. Some of you have worked in these areas where you can have a very capable digital radio. It can do even multi-hop. In the case of ZigBee, we don't need to do it here because we have only one hop to a networked infrastructure. But it's a very convenient standard where any kind of wearable device can start to talk right away with a wireless to this infrastructure that we built out. It's a very low power standard, unlike 802.11 that we all know. The ZigBee 802.15.4 standard is much lower power. So it works very well for battery devices. This is Matt here interacting. Matt is the architect of the portals. He's interacting with one of them, early one that we have up. We've refined them a bit. You see them around. We added a power switch. We actually have a whole talk on privacy with these because we're putting video and audio in our environment. People are living with it. What do we do for privacy? The simplest thing is we put a power switch on it. Everybody sees as a lamp switch. You cut it. You can see the power dies. These things are actually on servo motors so they can pan and tilt. They just basically slump down and they're off. So that's the brute force kill. So people can feel comfortable. If they really want them off, they can turn them off. We have other logical ways of turning them off, either at the screen or we have little badges that can turn them off remotely, depending on your preference with the wireless. It's a whole area of research that would take a while to speak about. I'll just summarize it there. Of course, the other side of these portals can be in Second Life. And we've done two-way connections where you can actually run a Second Life client on this, but it's a little bit thick. We actually run it now on a server, scrape the screen, and run video on these. So we can make Second Life appear in the real world. You can look out the virtual portal, but then in Second Life you can look in through the portal. So these portals can again be like little wormholes sending rich media as well as sensor information to and from a virtual world. And of course in the virtual world you can arrange portals any way you want. So you can take a space that can be not connected, but it can maybe topically connected somehow. You can just, in the virtual world, even drag them around and arrange them and make a whole new kind of a space with connections into the real world coming kind of as you want to be arranged in virtual space. This is the first version of this that we had done, at least for the portals. This is work of Drew Harry, who's a student here at the Media Lab. He's looking at history here, where if you look at the front, you can get real-time audio and video if you're allowed to get it. But then as you look into the back, you can look into the past. So it's got like an hour or 2 hours worth of history you can begin to browse. These tell you if a person has been in front, because we have these little badges. And with the IR, you can tell if you're looking in front, and if you are, then it registers that you're there, and we can register identity and identity into the past by streaming here a graphic. So you're going back in time as you're going in this direction. And sensor data can also be manifested here. This little blue thing is reflecting activity data. You can see it a little bit better over here, actually. So this line on the bottom of our newest version is activity. I can show you a quick little video that shows what it's like to browse this environment. We've run it during sponsor meetings. Let me try this. So here's Drew's avatar flying through, and you can see the different portals, the way he's arranging them. This is going to the past. You can see the activity traces in blue, that's sound and motion. This is presence, and here he's asking for a video feed. So he's getting a video feed from one of the portals now in real time. And again, if we run the server, he can pop out on the other end. That's Namway interacting over there. So we've run this several times for meetings. We haven't sustainably run it on all the portals yet, although we have a virtual model now of both Media Lab buildings, the new one and this one. So we're going to populate that with data from the portals, and I want to aim to leave it on so we can go anywhere in the world and we can look at the Media Lab through this kind of a network, and hopefully even pop out through the portals if you want to make a presence or appear in a space. I've done lots of other work too, monitoring. This gets more to what you put on an animal, I guess, monitoring kinetics. But for us, we did it initially for dance. We did a whole project monitoring dancers by making shoes that had sensors. Then we did work with the gait lab at Mass General Hospital to monitor gait, do gait analysis with a little wearable sensor suite, because then you don't need a motion tracking lab. You can do it in a doctor's office or at home. It's becoming a real trend now. But then we were approached by the doctors that do sports medicine here in Boston at the Mass General Hospital. It's the doctors for the Red Sox and the Patriots. Most of you know these famous Boston sports teams. And in particular, we were asked to work with the Red Sox because they're frustrated with motion tracking systems, the optical systems, because they don't measure force and torque very well. You have to differentiate in position measurement twice. It's very noisy, whereas accelerometers and gyros measure that more or less directly. We can measure at a much higher rate. We can sample these easily to kilohertz, even higher, whereas they're stuck with their typical systems. The optical systems are about 200, 250 hertz, which is a bit slow for them, especially these extreme bursts of athletic activity a player can give. And they want to be able to set it up anywhere, on the mound, in the bullpen, at a moment's notice. Just throw these on the player and get some data. With optical tracking, it takes a long time to calibrate it and install it. It's got to pretty much stay in one place, and the vision can be fragile if the light changes. So we built this. This is the second generation system. We actually have a third generation that we built. It's got a little Nordic radio, and here we actually stream data back at a megabit per second from all the nodes. So we had flash memory on board. We've got 3 gyros. We've got 3 accelerometers. Actually, we have 6 gyros, 6 accelerometers, 3 low G, 3 high G of each. Because athletes, they move slowly when they wind up like an average person, but when they pitch or hit, it's a burst of extreme acceleration or rate. And you want to get resolution across this whole dynamic range. You may see this in some animal species, I would imagine too, of course. I mean, animals naturally are equivalent to athletes in many ways, if not surpassing them. So what we would like to get is a log accelerometer or a log gyro that maintains a constant % resolution across a wide range. They don't make those right now. Although I'm talking to analog devices right now about trying to do a custom run of one that we could play with. So we had to use 2 ranges, low and high. That's what we have on this. We've also got a magnetometer, so you can actually, if you have a stable magnetic field, look at joint angles. And again, in a ball field, it's pretty stable and it works pretty well. we got lots of data. We went down to spring training. We put them on players. You can see we put them on here. Theo Epstein at the Sox is a real statistics freak, and he's bought into this heavily now, and he wants us to do the whole team, have the trainers do it. So we worked on making the attachments simple. We're working with a guy that does orthotics, so you can actually quickly get attachments that can mold better to the human body, strap them on, strap them off, and we can get them on players quick. The schedule of players at spring training is very tight. We get very little time with them, so you have to be quick about getting our sensors on and off. But we've got it down now to about 5 minutes, and hopefully to be down to a couple of minutes with the new system when we go back. And again, we put the sensors more or less where we want. They want them to be a Band-Aid. Everybody, of course, in your community wants them to be very small too, and some people have done great work that way. We could have certainly do them on multi-chip modules, but it gets very expensive. So at this point, we can live with the bigger nodes as we refine what we want to do and then try to shrink the hardware. We've got lots of data too. I'm not going to show that, but we just published a paper in the Wearable Computing Conference comparing players, looking at forces and torques and stuff, and we're working hard on mining the data we have now for features that could be predictive. This is the new unit that we built, actually one we did with spring training last year. And the difference here really is that we have an SD card on board. We've got a more capable processor and stuff like that, but we've got a built-in SD card. So we can now store to flash memory constantly. Again, in your community, this may not be too unusual. And we use the radio only to synchronize, because you have to, for millisecond timing, you want to exactly know, within much less than a millisecond where the samples all line up. But you don't care necessarily about getting the data off in real time, because you're going to analyze it later anyway. You can pull a record off just to examine once in a while and make sure they work. But otherwise, we just write to flash memory. So we synchronize with the radio, write to flash memory, and at the end of the day, we pull the flash off, transfer it to the PC, and then we can break the data up and analyze it. So it's certainly a more convenient way to work if you just want to log data. And again, in your community, I'm sure that the ubiquitousness of low-cost extreme memory has had a huge impact on animal monitoring devices, and now we see it in sports medicine. This is probably the world's cheapest wireless sensor and lowest power. If you look in that corner of cheap, wireless, low power, we probably have the extreme point here pretty much. We built it for interactive entertainment in large groups. This is a little piezo cantilever. So when you jerk it, the cantilever moves a little bit. It gives you enough voltage to basically gate the CMOS timer on. It gives you a very narrow pulse of radio. We have a little single transistor RF transmitter here that gives you a little broadcast at 300 megahertz when you jerk it. So you can basically count the pulses to see what people are doing. Give them to people. We go to events where they have a dance event or something like that. And we can look at the density of pulses and get some idea of the rhythm and the amount of activity. And then we can map that onto content. So I'll show you a quick little bit of video about it. Turn on the audio. Actually, there is audio here. Let me see if this works. If it doesn't work, I'll just, you can listen to the speaker because it's not that important. But. Whoops. You would know better. Yeah, this is the headphone one here, but this is an odd jack. This is a mini jack. That's why it's not working. Yeah. It doesn't matter. I think for this, I can just put the microphone down and everybody can hear it. It's kind of amusing anyway. So here you can hear the density of hits. You can tell the amount of activity. You can hear the rhythm. So the data is noisy, but you can hear the structure. They're just people just trying to beat in synchrony. Every time you get a hit, you just make a little drum hit there. And here we have that data. We're driving a music engine. So this is active control of people. The more activity we see in the sensors, the more music we make. That tends to make them dance more. That makes more activity in the sensors. That makes more music. That makes them dance more. So it's kind of a positive feedback. So they go a little crazy here. This is a MIT dorm. They're not the best dancers, but of course, no alcohol was served. This is something that evolved into, and again, I think these very low power techniques are probably very relevant for nature monitoring, animal monitoring, so on and so forth. You start to put in these things and forget them. And they're very low cost. The sensors are more or less off the shelf. This is what we call the cargo net. So we took those ideas we had in that low power dance sensor, we moved it to something for active RFID and supply chain. So we added more sensors of the kind you want to use to monitor shipment of goods as they move back and forth. So we have, again, this little cantilever, piezo cantilever, directly waking up the system when you have a shock. We have a piezo microphone, so it doesn't need an amplifier. The signals are loud enough. If there's a loud sound like something dropping or a potential breach, you have enough signal easily to be able to wake the thing up directly. And then we have a light sensor. It wakes up directly if the light changes. If there's light, if you open the door, for instance, it'll wake up. And then we can put in a little radio sensor too. So if you get a burst of RF at 300 megahertz, it'll wake up as well. So from a car key fob, for instance, at several meters, it can wake up at about microampere sleep. The thresholds are all adjustable. So if it's waking up too much, it can make itself less sensitive. Still sensitive, just makes itself a little number. And then it can adapt as the stimulus goes away and make its threshold more sensitive again. So it's a way basically of keeping your battery life constant because you're not waking up all the time on trivial things but capturing the information. We have also a temperature humidity sensor, so every minute we wake up and we log that. We have a couple of different kinds of temperature humidity sensors on here. So you get a really good picture of what goes on, around the device that could be relevant, for example, to shipments, but you could think of something like this going into a nature environment too. This is shipping this device across the country in FedEx, and this isn't looking at the sensor data. I mean, you can look at that. It's certainly got a lot of structure. You can see here the thing being shaken and moved, and temperature, humidity, light, all of that. But here we're looking at power. So this is just how much energy it's taking from the battery as it's moving across the country. And it's taking, as you can see, under 8 microamperes average. So in a coin cell, this will be about 5 years. And it's logging the relevant data. You can see it's pulling current only when it's being moved through sorting facilities or being handled. Here it's being picked up, someone's walking with it. Here it's being delivered into the sort facility. Here it's on the plane, not much happens. It's kind of intriguing too to think about what happens when these things get really small, looking at the future of these technologies. There's roadmaps of various sorts around the world to make these into a chip, and they say already we'll have it. I don't think we're quite there, although we're not too far, I'd suspect. Within a couple of years you can make one of these sensor arrays probably onto a single chip pretty easily. This is a roadmap from Tyndall Institute in Ireland. Fraunhofer in Berlin has the same one. I'm sure countless places in the US have similar charts. And you think, what happens when you get something this small? It really changes the whole dynamic. And for us, we took, again, inspiration from nature. So we thought about mobility, trying to harvest, people think about harvesting energy. We thought for a mobile system, mobile sensor, why don't you harvest mobility the way nature does, right? So you look at ticks and fleas. They also harvest energy, which is much harder to do from a human for a mechanical construct at this point. But we can certainly harvest mobility. If you see a host nearby, you can jump and grapple. That could be a vehicle, maybe it could be an animal. And then you can drop off somewhere else and then hop on again. So you mean to hop rides and eventually get more or less where you want. Or you can think of it like a burr. This is the other model in nature. And I wouldn't be surprised if people haven't done animal tags this way, where you have an adhesive and the animal basically, or in this case the human, will pick it up because they sit down on a chair and they can move around with it. I'll show a very quick video. I'm almost out of time, but I'll go very fast here. So this is the active node, and let me start it. That's better. So it's winding a spring. It has a full sensor node. It's got a little radio. It's got sensors on it, and it can launch. At this point, it doesn't self-right. I mean, you have to do a lot of work to make it mechanically working, but in principle, it functions. This is a primitive grappling actuator that we built on it. You'll see in a second. There's a little infrared proximity sensor too. So that's the grappling actuator. If it sees a nearby host, it'll latch. Of course, you could do that better, but it did latch. And it's looking for light. So when it sees light, in this case, beyond a certain threshold, it will delatch. So Matt turns the light on, and it's going to let go. So it moved itself. I mean, you could do it better, but the idea is all there. This is the passive node. And I wouldn't be surprised. I'd be interested in some of you maybe in the break and tell me stories about people who've done things like this in the animal world. He coated the same node with a silicone adhesive. And I'm putting it fast forward here. So there's Tara sitting down. It prefers the fresh bond, so it sticks to her shirt. And now she's transporting the node. And if we made it flat, we could probably get away with this a bit better. And she sits and it's transferred. But it has an actuator. There's a pager motor on these. And that gives enough energy to break the adhesive bond. So if it wants to let go, it can just vibrate. So now it's looking for light. It sees light, it'll drop off. So some of the applications in the animal world, I wouldn't be surprised if they don't exist already, so I'd be curious to know about it. This led to nature for us in a weird way. Some of you may know this guy. We were visited in 2004 spontaneously by Dr. Martin Nawia from Harvard Dental School. He's a dentist, but he's got kind of a Moby Dick fascination with narwhals because the tusk is actually a tooth. And he was just totally fascinated with it. People know very little about it, mysterious, and he was just obsessed with narwhal teeth. So he got us interested too. He brought tusks over, we talked, and he goes on periodic expeditions. So we actually took our parasitic mobility sensor, changed some of the things, put in a salinity sensor, put it in a waterproof package, did lots of other things, put an audio sensor on it. Actually, already had an audio sensor on it. And built several of these for narwhals. And indeed, Martin brought them up to the Arctic on an expedition with the Inuit. They corralled narwhals. They put these on the tusks, and some of them actually got off. Unfortunately, we only recovered one of them, and there wasn't any significant data in it. So at that point, we let it go. You guys know very well how hard it is to do something like this. Not easy. So what we did is we took our stuff that we did and transferred it to a company called Habit Research and pointed Martin to them and let them go and try to refine what we did into a better package. This is the last thing I'm going to talk about. We do a lot of badges at the Media Lab. Again, badges, you can identify somebody through infrared. In this case, there's a little infrared transceiver here. We have a dynamic display, so instead of just a static badge that has your name, it can say lots of things. And we have a radio on board. We have sensors, so we can actually begin to look at what people do, lots of memory. So the display can give you information. Here, at events in this room, it would tell you to return to the auditorium. The talks are starting, drinks are being served. Or you can send a message to an individual, and you can see it on somebody else's badge. If you face somebody else, you'd see your message on their badge, because you never look at your own badge. And we also, actually in this room, use them for timekeeping cues. If someone was talking too long, the badges would all flash the warnings that you're out of time. Very, very effective, actually. I have video, there's no time to show it. You could also bookmark. So if you face somebody else, you're interested in this person, you could push a button and bookmark that you're interested in the person, exchange a business card. Or you could bookmark a demo. We had little tags on demos. If you like the demo, you face the demo, push a button, you bookmark the demo. And after the meeting, you get a list of people you bookmarked on a website, and then you'd see the demos. This is Joe Brand from Steelcase. He's very social. This is a visitor from Fraunhofer Institute in Berlin. He just bookmarked their colleagues, his colleagues, and some demos. So you can see already human behavior changing just from simple data. We had lots of sensors, though. So we had the accelerometers, we had audio on all the visitors. And you could see this whole structure of the event that we had. Here they were picked up their badge outside. Here they sat in the auditorium. This is the coffee break. This is talks in the auditorium. This is lunch, more talks, and that's open house. So you can see it just by putting all the data together. It breaks out. Even the audio, it breaks out because the behavior is collective. They may depend on where you're sitting in the auditorium with the audio, but if you look at the collective behavior, it just comes out. Do people fidget more in an auditorium the longer a talk goes on? The answer we saw, we had accelerometers on all the people. And yeah, they tend to. So you can see as the talk goes on longer, you tend to get more fidgeting. It's statistically significant, not strong, but there's a correlation. This is the thing that really surprised us. Can you predict that people are interested before they even push this button? If they bookmark, you know they're going to be interested in somebody. And could we predict that was going to be true before they even pushed their button? Just by looking at the accelerometers, how they were moving, how much they were talking, how much time they spent face-to-face. Simple data. The answer is yes. With better than 80% accuracy, we could separate these classes. With a simple linear classifier, we could tell whether people were interested or not before they would express the interest. So people change their behavior as they get interested. You can read off this body language in some situations with fairly simple sensors. This is a collaboration with Sandy Pentland's group. And then we asked the other question, can you tell that people are affiliated just with simple sensors? With the infrared, yeah, of course, people spend more time face-to-face if they know each other. But what surprised us, you could do it with correlated motion. People that know each other tend to move in synchrony when they're together. And by looking at this correlated motion, we could pull out affiliation actually fairly well. Here, this is a scatter plot, and points are closer together. These are badge wearers. If they had more correlation in their motion, you can see the companies tend to be together. NTT Comware, they walk together. Telenor walk together. You tend to see this clustering. This led to animals. One of my main students on the project, Ryan Aylward, got his master's, and instead of going for the PhD, I tried to encourage him. He did a great job. Stay. No, I want to start a company. So got together with one of the guys who was doing the analysis of the badge data and a few colleagues, and they formed this company some of you may know called Sniff Labs. And they built a tag for dogs, urban dogs. And it has the sensors we have in the bat. It has an accelerometer so it can tell how much they're moving, and you get this whole pattern of the dog's activity. You can do analysis to break out the dog's routine based on simple signatures from the accelerometers. And it's got infrared. So if the dogs are facing each other, you know what dog saw what dog. So if these dogs all have these things and you give them to a dog walker, it's kind of aimed at the dog walker culture, I guess. You can tell afterward by downloading the data from the badge, what dogs your dog saw. Maybe you can start to do epidemiology with this too. I don't know. But they have a business. It's still existing. You can still buy it, and maybe they start a trend. This is the last thing. It's another badge we're doing. We have these portals we're using for another system that could be relevant for the animal world potentially too. Once you have all this data, how do you really query it is a big question. And we've got this rich sources of data from our environment, including audio and video. How can we ask questions about it and get content put together? Can we basically give the system a story in human terms and have video come back that reflects what we're saying? So my student Matt is trying to do that. We have wearable sensors that will basically pull out these social cues. He's trying to pull it up into an affect space or a narrative space, again, using some analysis and some machine learning. And he wants to put a query in terms of the story framework into the system. So you can actually ask it about how people that have these wearables are behaving, or give it a whole story where we had this kind of interaction, then this happened, and then see the video that best fits that start to appear. So we have a little wrist-worn sensor. It's got inertial sensors. It's got a galvanic skim response. It's got a compass and radio, little display. And we've got our new badge. It goes up here. It's very small. It has an OLED display, but it's got a microphone to analyze the voice. Again, accelerometers, gyros, all of those things to get into body language and then infrared. So there's Matt wearing his new badge. We made several of these. We're going to start running it in the next few weeks here. So again, the cameras are on the nodes around the building, and as we know, when people come by with the infrared and with the wireless, and then we can start recording video, and we label the video with data from the wearable. This is a video. Do I have time to show one video? This is the last thing. So this is the last thing I'll show. We didn't, the last sponsor meeting that we had in the spring, we didn't have the wearable sensors running with the system. We've got them now. We only had the sensors on the nodes though, but there were sensors on the spinner nodes. We had light sensors, we had motion sensors, microphones. So we could have some sensors. We're taking audio and video. Could we take just the data from the sensors and then go through Matt's spinner analysis and put together the video clips that best fit a story? So we could go in with the story input and get the video coming out that fits it. And he used a simple arc based on those sensors where he'd start with bright and calm scenes as if, it's the morning. And then he'd transition gradually to scenes that were more active, that had more motion and audio, so more people. And then abruptly transition to dark and calm scenes as if it's the end of the day. So he just went in with this query, and the system pulled these video clips out automatically and put them together. And he had music that he fit to the timeline. So this is a full sponsor meeting day at the Media Lab. It's compressed through Matt's spinner system. Okay. So here it's the morning. There's asking for bright and calm scenes. So it tends to give you scenes that are typically earlier in the day or when people aren't around and it's bright. Again, the cameras can point anywhere. Our cameras will pan and tilt now. Starting to get some activity. So more and more activity is coming in because he's asking for scenes that have more. So now it's going to threshold. So now it's asking for dark and calm scenes. And of course, there's the automatic exposure on the camera. The light sensor will give actually the true darkness. So there's a bit of a disparity, but they tend to be darker here. So you can see the basic idea. At this point, when we capture all this rich input, we can start going in with something that could begin to be phrased in more meaningful terms and see the results come back, assembled as how we ask for them. And projecting that up into human behavior would be the next phase that we're doing with the wearable sensors. And I would think for nature, such things certainly could be useful tools too. Okay, thank you very much.